Okay.
Okay. So don't worry. It's really not long. It's really, I'm trying to explain this on almost elementary school level. Okay. I want to make sure.
Yep.
Basically,
Yeah. No,
my
that's the
10-year-old
best.
understand. Okay.
Yeah. I like starting from scratch.
Just to be clear, because people always think, oh, this is so complicated. And it's actually easier. It's so, once you see, it's like, oh my God, you're going to do a facepalm, you know? And just to set the context real quick. So, I mean, there are all these interpretations of quantum mechanics, right? And my goal is really to understand the mechanics of quantum mechanics. So this is different from all of the other models, I think, because basically this is based on the idea that there actually is a medium. There are waves, and there's nothing but waves. We don't need. It's kind of related to the palette wave, except in the palette wave theory, you have the wave and a particle on top of it.
Yeah.
And
no, the wave has to be particle has to be a wave as well.
Yeah, exactly. And to me, I call it neoclassical because it's just based on a classical model. And to me, it's much simpler because it actually goes underneath and explains the mechanics. So just really briefly, in this model, right, we have some kind of what people call space-time fabric and fields and all that. Basically, in this model, there is actually a real medium, whatever it is, probably some kind of elastic solid. Might not be that, but at least it works out with that one. And it's an optical mechanical analogy. So there's no space. So there's no space-time. It's 3D space. Okay. Time is absolutely this. I'm gonna get on a lot of people gonna say what, but I'll explain this in a minute.
What I say, I say time is an emergent property of change. That's my
exactly.
statement. And that's all it is. So if things are changing in your medium, then that would be a manifestation of time.
And just also be clear, and I won't go through these details, but all the math is equivalent to the standard, way the mainstream interprets it. So that I'm not saying anything is wrong. This is all equivalent, and there are papers about this. So the space density model is mathematically equivalent to the Minkowski space-time and all that. And here in this, the nice thing about this is that special relativity emerges, and I'll explain that. Also, just a brief note, what we just talked about before. In this one, particles are really just a way how we measure things. There are actually no particles. Even photons, right? It's just a way how we measure photons, in quotes. So how we measure the wave, first to get back to your presentation, is, what does that mean when we measure a photon? It usually means that we elevate, an electron to a higher energy level. And that depends, and that is, of course, an event. That's something, the frequency matches. That's an event that happens. That frequency matches perfectly, lifts the electron, in quotes, the wave to a higher level. And that's when we detect in the detector, but that's what we detect. So it looks like we have detected something, but it's not the wave we are detecting. It's just that interaction between the wave and the electron, just as a side.
Right. Do you think quantization is a result of the detector?
Oh, absolutely. Yeah, absolutely.
Good.
Of course, you could have an event, and also how is light emitted, right? A light is emitted, and you have an electron in some atom. It's excited, right? And then the energy it drops one level with a certain frequency. That's exactly when you get that one wave with that exact frequency that spreads out in all directions.
Yeah.
Right. That's why it's quantized, because the electron has specific levels. If you look at the Schrodinger's wave equation, the orbitals and all that, right? That's the reason. But when we think about other light waves, I mean, radio, for instance, are also light waves, which many people may not even realize. When we make radio waves, well, those aren't quantized. We can make the radio waves in any way we want. There's no reason for them to be quantized, actually.
Exactly. Yeah.
Anyway, that's another topic, but people should think about that.
No, I understand that. Yeah.
It's how in nature, I guess, all sources that we know of, at least I can think of, are quantized events, usually from electrons. But there could be other ways, light waves or like radio, that's not quantized, But anyway, I
agree.
Tangent. So for this special relativity, only thing really you have to know, and I mean it's the only thing you need to know. And remember, the speed of a wave in a medium is mostly constant. I say mostly because, yeah, if you look at air, yeah, sure,
Yeah.
the speed of sound, it depends on the temperature and the pressure.
Yeah.
Yeah, but given
Yeah.
same
If the
temperature,
conditions are consistent, if
yeah,
the
it's
gradient, if there's
same.
no like gradient or whatever, yeah.
Yeah, and the same, and there's different wave speeds. Water, it's a little more. And
Yeah.
diamond, it's 11,000 meters per second. That's quite a
Yeah.
lot.
Yeah.
But speed of
Yeah.
light is as you know.
What is
So
what? Okay, I'm going to quiz you just for a second. What do you think the speed of propagation of ultrasound waves are in the human body?
the human body, I guess, would be somewhat watery. So maybe it has also salt in it and stuff. So I would say maybe 800 meters per second.
No, it's about 1530. It's a
Oh,
little
okay.
bit
So it's
faster.
actually
It's a little
actually
bit
more than water.
faster. So the
Interesting.
elastic properties, I think, of the human body make it a little bit faster. Even though
Oh,
it's
that's my
more
next
dense than
slide.
water,
Interesting.
it's the elastic. People forget about the elastic properties.
Yeah.
Actually, you have the
This
elastic properties over the
exactly.
yeah. So
Exactly. So the question
yeah.
is, how can you what properties define that speed of that wave, right?
Yeah, and that's
there's
the
so much
elastic
more
properties divided by the density of the
different
mass
things
of
how
the particles in the medium. Yeah.
formulated. It has to do with the density also,
Yep.
and with
Yep.
the stiffness. So basically, the stiffer something, like a diamond is very stiff, right? You can imagine it has a much higher speed, and the less dense it is, also the higher the speed is.
Yeah.
So here are some examples. So if we imagine, space, time, or fabric of space, or whatever you want to call it, as some kind of medium, I was just curious to imagine what would that be like. Is it like a diamond? Is it like water? And of course, the speed of light is so large, and I put it in kilometers per second here. So it would have to be, if you compare to diamond, you would have to be a lot more stiff than diamond, right? And a lot less dense.
Not necessarily. Can I
It could
interrupt
be,
again?
yeah,
Sorry.
yeah.
Okay.
We don't know which way
Because
it is, right? Yeah.
there are two components to calculating the speed of a wave, and one is the
Mhm.
density, which is in the denominator, and the
Exactly. Yeah.
elastic properties, which are in the numerator of the calculation, right? Where you do the square root of
Yeah,
the
yeah.
stiffness divided by the
Exactly.
density. So the
Could be
density,
either.
the stiffness can be very, 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 if the stiffness is very, very, very high and the density is very, very, very low, then you could have a really fast speed of light.
Yeah.
Right.
Yeah,
So
you
it's
can also
not
have a
just,
very dense material and even stiffer. You can we
yeah,
don't know. I don't know of any experiment that could tell. I
no,
don't think we know. I also have
we
to
don't.
keep it, and
We can
I
guess.
think
We can make an educated guess.
it's just an example. Like if it
Yep.
were like 1 kilometer, 1 kilogram per cubic meter, very, very light material, then it would be, that would be the stiffness basically. So
Yep.
and that's the only thing you have to remember is the
Yep.
speed is constant. So now I'm going actually to elementary school. I'm making an analogy, and literally it's as simple as it is. It's not more complicated, and even it's an analogy, you're going to see how we get to the real world really easily. Okay.
Okay.
I'm just laughing because it's really simple. So imagine we have this boat somewhere on a lake, and we're building this water clock. So this is a clock made out of water waves. So we have this little rock here, and you can see my mouse, right?
Yep.
There's a little rock we dip in, and then when you dip in the rock, you have this wave that spreads at the speed of the wave. Okay,
Yep.
C, we call it C, all in all directions, and then at some point it's gonna hit the bell, and it makes ding, and that's what we call. This is one tick of our water clock, right? We call that.
Nice. I
That's
like
one
the
tick.
analogy. It's cool. Yeah.
And we observe. We are like standing outside this little universe. Of course, we have our own clocks, right? Independent of that, we can say, well, that one tick is 4 seconds. But these water people, let's say, they have that water clock. They only have that water clock. They don't have another real clock like we do. They only
Yep.
have this clock. Okay. So, and I think it's obvious what's going to happen next, right? So what happens? So now it is again the same thing. The boat is stationary, and I kind of simplified that wave with an arrow, but it's going in all directions, right?
Yep. That's the direction going. That's the part of the wave going towards the bell.
Yeah, exactly. Now, what happens if we start to move the boat? So we dip the rock in the water. And at that point, as when we dip the rock in the water, at that point, actually before, it doesn't matter. The boat moves to the right a certain velocity. Well, now it's a trivial question. Is it going to take the same amount of time to reach the bell, or is it going to take longer or shorter, right? And you can see it. Well, the wave has to travel further because the boat is moving away from the wave, so it's a longer path. Well, yeah, it's gonna be, maybe it's not gonna be 6 seconds, right? This was maybe 4 seconds, and now it's 6 seconds. But these people on the boat, they wouldn't know. Let's say they're blind or something. I don't know. That for them, it's still that one tick, right? That one tick. And now we go to a high school level. And I think that's the only thing we need to know is basically I cannot say the word Pythagoras because I'm German and we pronounce it differently. So all we need to do now is have an equation that with a triangle where we can see
very simple.
So this one was 4 seconds. Let's say it took 4 seconds times the wave speed. And this, of course, this is the speed of the boat, right? And then we can see how long will it take. So, and then, I mean, that's it. And then when you just do that, I mean, step by step.
Exactly Pythagoras. It's exactly the formula that we're used to seeing. Yeah.
I spelled it out in detail. You get the Lorentz factor. Okay.
Yep.
I mean, and of course you'll say, well, that's just we are not, boats or anything, but still, so far what we've learned, right? We can see now that if you have clocks that are based on waves, then moving clocks, they tick more slowly. That's far, that's what we know, right?
Yeah.
Let's see now, next level. Let's see, where am I? Yeah, and this is just, so people might start to complain and say, what is this wave thing, and I just trying to say this is not so absurd as some people might make it sound like, because, even, Schrödinger always said, he interprets this as a real wave, electrons, for instance, instead of a probability only. So it's not something crazy, that we are just thinking of. I mean, lots of, even Einstein, he has also famously said, and people can look it up online. It's not a made up thing. He gave that speech, right, where he's also saying that, he said that, the space is endowed with the physical qualities, and he even said that space without ether is unthinkable. So people always quote Einstein's name, or Einstein proved there's no absolute whatever. No, he did not. What he showed, we don't need it to calculate anything. Sure, like I don't need to evoke some absolute frame of reference to calculate anything, but it doesn't mean there doesn't exist. And just a side note, because people always complain about this. And I think
I agree. I saw the video where he said that. I literally saw the video where he said that. So
okay.
He said it. Yeah.
I think I don't have to go through all of this necessarily. This is just some examples from how people also use the equations for the optical analogy in doing optical black holes. So let me just go continue.
Ooh, I like that
now
picture.
Of course, I think that's AI. I probably asked AI to generate a picture. No, so the boat, of course, is a simple analogy. Now in the model that we're looking at, we're saying, well, light is composed of waves, but also matter is composed of waves. That means our clocks are made of waves. Our measuring sticks are composed of waves. Anything we have in our world is composed of waves, right?
Yeah.
So that's really important, because now basically we have exactly the same thing, except instead of a boat made out of wood, we have, say, spaceships or whatever. It could be aliens, doesn't matter. But these are also waves. We do have clocks that are waves, and like you can imagine a phonon clock, right? It's exactly 100%. The same story again. There's nothing new. It's the same thing, Of course, the difference with the standard interpretation is that the speed of light is constant in an absolute sense. And then people will like, oh my God, that's not possible. But because the thing is, even if it's constant in the absolute sense, the thing is we can never detect it because moving clocks are slower, right? Moving clocks are slower. And because, and I don't have a slide on this, but because when you have a moving object, imagine this is composed of waves, right? When the object is moving, the waves get also compressed because of the Doppler effect. So your measuring sticks get shorter as well, right?
Yeah.
Is that clear? Because, when you imagine we have, we have 10 waves. This is our measuring stick. When you move in a medium, then those waves, they get compressed because of the Doppler effect. It gets shorter, and it's like a conspiracy, but it's just the way it is. it gets shorter just as much as the time goes slower. It cancels each other out, and we will. It feels like a conspiracy because we will always measure the same speed of light.
Yeah.
Unfortunately, even though it's not, speed of light. If we could watch from the outside, okay, we are outside of this universe. We can see what's happening. We see that the speed of light is constant in that absolute frame of reference. But the observers inside also, they measure always the same thing, even though it's actually relative to them, it's not the same speed, but they always measure the same.
Yeah.
And
so in their frame of reference,
but it's the same thing, and it feels to me like it's trivial because the only thing you need to know is the speed of light. The speed of a wave is constant in medium, and if you have a medium, then special relativity is no longer so special. It's really an emergent thing. Any wave system has the same effect, the same observation. There's really nothing special about it. And also, I want to really give credit to Robert Close. He has this animation, and let's see, maybe I'm not sure if I can open this. So he actually had this. He also has a paper on this where he goes much more deep into the math. In all the details. He has animations. And and of course now there are all these people complaining about things like Mike Mickelson-Morley. So I just want to bring up that one because it keeps coming again and again.
Okay.
Just briefly, right?
It's going to come, so you might as well deal with it. Yeah.
It will come in the comments, for sure, 100%. So just briefly, they measured. They didn't measure. There was a null result. That means they couldn't measure Earth moving through the ether. The problem is at that time they still thought light might be a wave, but I thought like the measuring devices are actually particles moving through the ether, like you go through the water.
Yeah.
That's of course not case, right? If
that's not what we're thinking.
Talking about in this model, the apparatus is also made of waves, so it's not moving through this elastic solid. It's part of that wave, so it will get the length contraction, and then it cancels each other out. So this is actually compatible with. It's compatible with an ether when matter is also composed of waves.
Yep. There's a researcher named Robert Distinti that refers to that as the gift. It's actually a gift that the universe works this way, that we are, as you move, like if we were in a rocket ship, we're not going to feel any different laws of physics than if we, constant velocity, as if we're on Earth, as if we're on some other planet. He refers to that as the gift, which I thought was kind of cute. So I did a similar thought experiment using, I was talking about ultrasound and the speed of sound in human tissue. So in our lab, what we do is we build these phantoms and we try to mimic that same speed of sound of tissue. So we take something that's called gelatin, basically jello, agar we call it. It's like jello. And then we add stuff to it to make the speed of sound similar to what the speed of sound of tissue is, so we can test all of our 3D our ultrasound technologies, and we can mimic what would happen if we were actually we can make all our measurements, make sure our tracker devices are accurate and all our scanners are accurate, mimicking it. So I did a thought experiment kind of similar to what you're talking about, where I imagine, okay, I know what the speed of sound of agar is, so let's call that the speed of light in agar world.
Right.
And then I imagine that all the people in agar world were made of agar, and what would they experience? And it's exactly what you just said. The important thing is the people in agar world have to also be made of agar. then the waves will behave the same, anyway. So it's kind of not exactly what you're saying, but it's kind of like you have to be in the same context for relativity.
And the recent analogy, let me just briefly go to that slide. There's something called phonons that's called, sometimes you call particles.
They're called phonons in our world. We call them phonons.
And plasmons and polarities. And nobody in their right mind will say, oh, this is an actual particle, and this is, you can even do the double slit experiment with them, and nobody in their right mind would say, oh, the universe is splitting up in multiple universes because of phonons. No, you can watch it with a microscope. You can see it's a little wave. You can actually see it, and and the mass of the phonon is the same as the photon.
It's equal as
like,
HF. It's the same.
why would it be anyway? So
Yeah.
there's some
Yeah.
actually analogies. So one other thing that people will often say, well, oh, you have a preferred frame now. That's disaster. The thing is, we can't detect it, right? There's unfortunately, and I have myself thought I was so clever. Think of experiments that could detect it. You cannot, and maybe I'll do another video on that one. It doesn't mean that we can never detect it, right? And so people will say, well, then what's the point of this? You can never detect it. Why just get rid of it? Well, the thing is, if you get rid of it, well, you have all these paradoxes and the weirdness, and then you
It's
have
about the
time running
language.
different ways. This gives everything a cause, a reason, a root cause. Everything else can be derived from it, and it's so easy to understand. Like general relativity is basically just refraction. Duh, easy. Special relativity is trivial. The waves, we don't have to worry about, oh my god, it's a probability thing, but it's not real because there's no medium, so there's no wave. This probability sometimes suddenly turns into this particle. Like, you get rid of all this stuff.
And simplify the language.
It's philosophical maybe, but I mean, what's the point if you don't understand physics? I mean, if you don't understand how does all the reason, the cause, how can you make clever new predictions? I think if you actually understand the mechanics, now we can start to think, oh, well, if this is an elastic solid, and maybe we can come up with new wave shapes. Maybe we can come up with new experiments to do, right? I mean, I don't know. But if we have all this weirdness, how can you, if you can't make sense of it, if it's just shut up and calculate, how can you even, I'm just wondering how you could even make new predictions.
I 100% agree. What I always say on my YouTube channel is the problem is with the language. The physics is fine, but if the language could be better, then we can teach it to people faster and sooner. And like you say, we can innovate around it, because if we have a proper language that isn't confusing and isn't just sort of relegated to the super mathematicians, the only ones that can really understand it. If we can bring it down, like we can create a language that we can teach in high school or
totally. This is totally high school
and
level.
you're opening that door up to so many innovators that are geniuses out there that just, well, the geniuses are probably good at the complicated stuff, but you know what I mean? Like average people like me.
But also kids. I explained this to my kids.
Idea.
But I explained to the kids, they were like, she was like 15 or so. She's like, yeah, that's easy. What's the big deal? I'm like, okay. But she hasn't studied anything of that yet. So to her, she sees it very naively, and we talk about it a lot. And I think when people are young, they have creative ideas. She has
that's when you want to capture that.
Yeah, right. It's
for sure
nothing to be afraid of. So. And of course, I haven't finished this slide. Sorry about that one. But I do have a web page where I explain, because people say, oh, well, there's one thing that you cannot explain, right? Photoelectric effect. And I'm not going to go, this is a whole nother thing. Maybe I can do another video on this. But there are explanations that are wave-based classical. It has to do with the frequency and resonance effect. And there are multiple papers on it too. So this, just in case someone complains, I have it explained on a web page.
No, the photoelectric, to me, the photoelectric effect is better explained when you realize that what you're doing is you're breaking the binding energy of the electron to the metal, and that's all it is. So the electron is bound to the metal, and then you have to go above that binding energy, so you're breaking the binding energy. That's how I see it, and it works out mathematically too. So it is really when you say, what is the binding energy of a electron to a metal, whatever metal happens to be in the whatever metal they're using for the photoelectric effect, you'll see that you have to go above that binding energy. And then if you go even more above that binding energy, you actually set the electron into motion, right? So
there are some weird stuff, but it takes a little while to explain it. So I'll skip it because I haven't actually made the slides for that one. But basically that there are explanations, and people have written papers on this also. And this is basically what I was trying to say also. Like when we have this ether, what we can do, we can derive a lot of it already. So we have a lot of, like, multiple people have already derived special internal relativity from it, including all these people here. Also to give an acknowledgement, we have been able to derive the Rock and Schrödinger equation from this medium. The Maxwell equations can be derived from it, and so of course there's a few more things left, but so far it really makes everything a lot easier. And also I'll put it online as well. There's many references from people who have worked on this. Also, Donald Chang, he has written a whole book on that. So if you want to read this in case anyone's interested. And also Robert Close, he's a bit quiet, but he has written a whole book on this also, and he's very mathematical, but he has a very good introduction of the history of science, how this all happened, and he's very good in terms of math. I believe that his math is probably the most exact.
Good. Someone has to be good at math. It's not me.
It's dry. Like, it could be really dry, and I don't understand. I have to read it multiple times, some of the things, and I still don't get everything. So it's
good that you're in contact with him.
I'm trying to simplify things, basically. Yeah, there's also Ilya Schmelzer, a really super smart guy, even more mathematical, but he basically derived all the fermions from the standard model, all of them, using this elastic solid model as well.
Nice.
Unfortunately, his math is beyond, like, I would have to study 4 years to get it, but people tell me it's correct, so
okay. Well, maybe we can figure out how to simplify it.
With AI, my goal is, now that AI is getting better, to take these papers, like with Notebook LM, to give AI the papers, and then, please explain this to me step by step, and it's not all there yet, but it's getting there. I think maybe in a year or so. I'm putting out a lot of these podcasts, but also I want to do more of that stuff, like complicated papers, break it up and make it, basically, it's probably like 3 pages, turn it into 20 pages and make it
palatable. Yeah.
Exactly. So I'm just going to stop my screen sharing.
Yeah, I'm glad that you're using AI, that you appreciate the value of AI and what it can do for you.
Except you, but otherwise it's my best friend now.
That's cool, because I know I get people saying, "Oh, AI." Well, we had this discussion before. AI, well, you might as well go ask your next door neighbor, and it's like, okay, what if my next door neighbor's a mathematician? Like, AI is quite spectacular for doing a lot of the things that we're doing, like writing chunks of code, and, like you say, taking a paper and rewriting it in a way that's palatable to you. And then you can ask,
like the simulation. I uploaded this today. I don't know if you saw it. I have this simulation.
I didn't get a chance to look at it yet, but I will.
It's spherical waves. It's spherical vector waves, spherical scalar waves. It's spin 1/2, but all in the elastic solid model. And GPT helped me a lot to write the code, because all these mathematical functions.
I had a few slides to work on this morning, so I didn't get a chance to look at it, but I'm very excited.
It's a lot of math, right? So I take this Wikipedia page, turn it please into JavaScript, and I made sure it's correct. Okay, I mean, multiple rounds and verification and everything. Nice. So
is this code shareable, or are you sharing it, or?
Oh yeah. It's the link. It's shareable. You can edit, even you can take the code. It's the point is just you can play with it. People can visualize stuff.